Welcome back to Java Internals Crashcasts. I'm Sheila, and today we're continuing our exploration of the java.util.concurrent package. In our previous episode, we covered the overview and motivation behind this package. Now we're diving into the specific concurrency problems it helps solve. Victor, are you ready to unravel these tricky issues?
Absolutely, Sheila. I'm excited to discuss these common concurrency pitfalls and how Java helps developers tackle them. Before we start, listeners, make sure you're familiar with basic multi-threading concepts, as we'll be building on that foundation.
Great point, Victor. Now, let's kick things off with a quiz question for our listeners. Here's a scenario. You have a shared counter that multiple threads increment. Sometimes the final count is less than expected. What type of concurrency problem is this?
Ooh, that's a great question, Sheila. It really gets to the heart of one of the most common issues in concurrent programming. Listeners, think about what happens when multiple threads try to modify the same data simultaneously. We'll reveal the answer at the end of the episode, so stay tuned.
All right, let's start with the basics. Victor, can you explain what a race condition is?
Certainly. A race condition occurs when the behavior of a program depends on the relative timing of events, especially when multiple threads access shared data. Imagine two chefs trying to add salt to a dish at the same time. They might end up over-salting it because neither realized the other was adding salt too.
That's a great analogy. So, how does java.util.concurrent help prevent race conditions?
The package provides several tools, but one of the most useful is the atomic classes. Like atomic integer, these classes ensure that operations on shared variables are performed atomically, without interference from other threads.
I see. Moving on to something that sounds scarier, deadlocks. What exactly is a deadlock, Victor?
A deadlock is when two or more threads are unable to proceed because each is waiting for the other to release a resource. Think of it as two polite people at a doorway, each insisting the other go first. They're stuck.
Oh, that's a funny image, but I imagine deadlocks are no laughing matter in real systems. How does java.util.concurrent address this issue?
You're right, deadlocks can be serious. The package provides higher-level synchronization utilities like reentrant lock and semaphore that can help manage resource access more safely. They include features like try-lock, with timeouts, which can help threads avoid getting stuck indefinitely.
That makes sense. Now, I've heard the term thread starvation before. Is that related to deadlocks?
Good question. Thread starvation is different from deadlocks. It occurs when a thread is unable to gain regular access to shared resources and is unable to make progress. This can happen if other threads hog the resources. It's like being in a busy restaurant where the waiter never gets to your table because they're always serving other customers.
I hate when that happens at restaurants. How does Java help prevent this?
Java's concurrent utilities include fair locking mechanisms. For example, the reentrant lock can be created with a fairness parameter, ensuring that threads are given access to the lock in the order they requested it.
Interesting. You also mentioned liveness earlier. Is that related to thread starvation?
Liveness is a broader concept that includes thread starvation. It refers to the ability of a program to execute in a timely manner. Deadlock is an extreme form of liveness failure, where the program ceases to make progress entirely.
Got it. Lastly, can you explain what memory consistency errors are? They sound complicated.
They can be tricky, Sheila. Memory consistency errors occur when different threads have inconsistent views of the same data. It's like if you and I were looking at the same billboard but somehow saw different advertisements. Java's memory model and the synchronized keyword help prevent these, but java.util.concurrent provides even more tools like the volatile keyword and atomic classes to ensure consistent views of data across threads.
That's a lot to take in. Before we wrap up, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Certainly. The scenario described in our quiz question is a classic example of a race condition. Multiple threads incrementing a shared counter can lead to lost updates if not properly synchronized, resulting in a final count lower than expected.
Thank you, Victor. To summarize today's episode, we've covered race conditions, deadlocks, thread starvation, liveness issues, and memory consistency errors. We've seen how java.util.concurrent provides tools like atomic classes, advanced locks, and synchronization utilities to help solve these problems.
Exactly, Sheila. Remember, concurrent programming is powerful, but requires careful consideration of these potential pitfalls.
In our next episode, we'll be diving into the key interfaces and classes in java.util.concurrent. Don't miss it. And listeners, if you're enjoying our Java Internals Crashcasts, please subscribe and leave us a rating. Your support helps us continue creating this content. Until next time, happy coding.